All right, in this video I'm going to be talking about autonomous equations, equilibrium solutions, and stability, instability, semi-stability of solutions for differential equations. All right, so first I need to tell you what an autonomous differential equation is. So a differential equation is autonomous if it only deals in the dependent variable. So if we have y prime equals some function of y, that's an autonomous differential equation. And we've actually seen an autonomous differential equation before. Last year and in this class, we talked about the logistic differential equation. We know about that from Cal BC. We're actually pretty fluent in some of the things about it. And I think what I want to do right now is just kind of, oh, no, I need to tell you about what an equilibrium solution is. Okay, so an equilibrium solution is like a constant solution. So, you know, say if our initial population in the logistic case had been the carrying capacity, it's probably just going to hold steady at the carrying capacity. Also, if we start off with a population 0, it's likely to stay 0. Okay, so an equilibrium solution, let me say, okay, I'm going to say the curve y of t equals some number y0 is an equilibrium solution if f of y0, this f, is equal to 0. And that would be if f of y0 is equal to 0. So that's an equilibrium solution. Okay. Now, let me point out a couple of an autonomous differential equation and an equilibrium solution. Right? That would be the logistic differential equation. This is where y prime is equal to some number times y times some other number minus y. Okay. In AP Calculus, you learned about what the shape of the solution curve looked like depending on the initial condition. But for now, I think I want to kind of look at the slope field for this thing, right? Because that's what the graph of y prime is k times y times l minus y, right? It's a slope field. So I've got L here, let's say, and I don't want to give too many marks because then that'll make my slope field look worse. So maybe 4 should be fine. All right, and so what happened was if we started off here, we wanted an S. So, you know, maybe we started off pretty flat, and then we got a little steeper, and then our steepest was halfway. And then we got less steep to the point where we were pretty much nearly flat. Okay, that's not the best slope field I've ever drawn, but you can see, you can kind of get the S pattern out of it. And then over here, we kind of saw the same thing if we had the die off. If our initial condition was too large, we were also going to approach that. And the solutions, right, we saw that if the initial population was less than half the carrying capacity, we get that full nice S. And we knew if we had too much of an initial population, right, there weren't enough resources, there was going to be some die-off, and it was going to approach over here. Now the fact that both of these types of solutions are approaching this horizontal asymptote is something we're going to be interested in today. And then I also should point out that when the population was negative, which is not a situation we really had an interpretation for, but I do want to talk about it, that made y prime negative, and so we would end up with something like this, like going like this. Okay, and then maybe I'll come back to y equals 0 in a little bit. So this is autonomous because this is a y prime in terms of only y. The only variable I'm saying is y. And then we have equilibrium solutions. That would be y equals L is one equilibrium solution, right? because if I plug in L for y, I'm going to get, where is it, right here, I'm going to get y prime equals 0. Okay, that's the definition of an equilibrium solution. We've also got y equals 0 as another equilibrium solution, right? Because if you start off with no population, you're going to keep going with no population. Okay? And I think that I'm going to leave it at that for now. Okay? And then I'm going to talk about stable, semi-stable, and unstable. Okay, so like I said earlier, the fact that these, with the initial condition on either side of L, both of those curves are kind of coming towards L as t goes towards infinity, that's something we're interested in, right? So I'm going to say, I want to show this. All right, so for stable, suppose I've got an equilibrium solution. Why not, like I was saying. And the idea with this stable is that with, initial conditions near this y0, we're going to see them going towards y0, right? And so really what this kind of looks like is, all of these curves are kind of converging onto the horizontal asymptote y equals y naught. And, I don't want to draw too many pictures in here and make it too noisy, but we're seeing this is stable where they're kind of all coming together. Unstable would be where they're exploding away from the steady state, the equilibrium solution. Okay. So unstable is going to be where I've got myself an equilibrium solution, but solution curves with initial conditions nearby that equilibrium, they're going away from the equilibrium. Let's see, probably like that, right? And then we'd see the same thing over here. Not the best drawing ever, but you can see they're away, right? And then there's going to be a semi-stable. And that can, as you might expect, that's going to be on one side we're going towards the equilibrium, and on the other side we're going away from it. And of course that can take two different, forms, right? We could maybe over here on top for these values we're going towards the equilibrium. And for, initial conditions on the other side, we're going like that. Okay, so that would be semi-stable. Okay. To use that terminology over here, I'm going to say that y equals L is stable and y equals 0 is unstable. Because I've already drawn one of the curves for, initial condition near y equals 0. But maybe I'll go even closer and we'll see that that's going that way, and if I was on this side, I'd be going that way also. And so these are going away from y equals 0, and I'd say that's unstable. Okay? And now in order to show you an example of something that's semi-stable, I believe I am going to need to cook up a new example. Okay? And then maybe I'll show you like some, kind of some machinery you could use to make that determination on just some general differential equation. All right, so the next example I want to do is y prime is 1 minus y times y minus 4 squared. Y prime equals 1 minus y times y minus 4 to the 2. Okay. This is an autonomous differential equation, and y prime only depending on y, and we'll be able to, kind of write down our equilibrium solutions and determine if they're stable or unstable, which is really like kind of our goal right now. All right, so my equilibrium solutions are going to be y equals 1, y equals 0, and y equals 4. what we're going to want to do is we're going to kind of want to make a little number line, like a little y-axis. And then we're going to test points on either side, which should definitely be familiar if you're a veteran of AP Calculus. And so maybe I'll do that over here. I've got 0, 1, and 4. And what I need to do is I need to find out what is kind of like the sign of y prime on these little regions. So what I'm going to do is I'm going to take a number less than 0, like say -1. And I'll have positive, negative. This is always going to be positive. So I've got positive, negative, that makes negative. Okay, so I'll just put a little negative right there. Between 0 and 1, I'm going to choose a half, right? Positive, positive, positive. Between 1 and 4, I'll choose 2. I'll have negative, positive, positive. And something bigger than 4, like let's say 10, negative, positive, positive. All right, so I've got that there. And what we're really going to be doing is we're going to say, okay, positive means I'm going up. Okay, so I'm going to be going up here. And I'll also be going up as I approach 1. And the fact that I'm interested in kind of 2 different points is why I'm drawing 2 different arrows here, right? Now, between 1 and 4, I'm going to be going down because I'm seeing y prime is negative. Okay. And I'm going to see that here just the same. Okay. For y bigger than 4, I really only care what's happening as I approach 4, so that'll be going down. And over here, it's negative, so I'm going to be going down there. Okay. All right. So now let's again kind of get into the point where I'm going to need to, it's a little noisy. I'm not sure if you can tell exactly what you're supposed to see from this. So I'm going to start with y equals 1. And I'm going to kind of take this. Maybe I'll just kind of circle it like that and bring it over here. So what I've got is at 1, they're coming together, okay? And if we were to like extend this to an actual graph, what we'd be seeing is the solution curves are kind of like merging together. Okay, they're going towards one another. That is going to be stable. Okay? So when I see both of these arrows kind of pointing down on y equals 1, I'll know that that is stable. Then for y equals 0, I'll just kind of be over here, take all of that and bring it over there and kind of reproduce it. And then I'll have 0 here. At 0, I was going away. And that would be the same thing I was seeing down here at 0, right? They're going away. Solution curves that start below it are going down, and solution curves that start above it are going up. Right, so we're going to consider this unstable. Okay. And then, well, y equals 4, that's the one that's going to be semi-stable, mainly because I was, kind of cooking up an example just to get you one that was semi-stable. But I'll look over here, I'll take all of this, and I'll go down here, draw you the picture. At 4, we saw both of them were going down, right? And mainly because we had no sign change because of that, the square. But if I'm seeing down and down, or negative and negative, or just kind of a repeated sign, I know that's going to be semi-stable. Okay? And both of these are going down. And so it means that, for above, we're coming down on 4, but below 4, we're going away to something less. And so this would be what I would call semi-stable. Okay. I'm not exactly sure where this is going to come up again in this class, if it's going to be this class or maybe it's just some other situation or some sort of scientific situation where you need to be interested in the relative stability of solutions to autonomous differential equations. But this is what I mean when I talk about an autonomous differential equation, an equilibrium solution, or the stability or the relative stability of solutions.